Hi, my name is Calvin, and welcome to my Comp 3132 Machine Learning Assignment 1 video. In this video, we're using TensorFlow, specifically the fashion MNIST is not necessarily TensorFlow, but we're using a fashion MNIST dataset, and we're using TensorFlow along with Keras to analyze our data and make predictions based upon images of clothing such as a pullover sweater, a shoe, a shirt, or even a pair of jeans. That being said, let's get into it. So the first thing that we're going to want to do for this assignment is we're going to want to import some of our libraries. So like I said earlier, we're going to be using Keras and TensorFlow. So from Keras, from the datasets, we're importing our fashion MNIST dataset. That's what contains all the articles of clothing and all the pictures along with the labels that we are going to be learning from. So you would run that there. And then next, what we're doing is we're just going to check all the dimensions of the fashion MNIST dataset. So we're going to load our data. We're taking our training images, training labels, the test images, and the test labels, and we're just getting it from our fashion MNIST dataset right there. And to get our dimensions, you're going to see the number of dimensions for the training images is 3, 1 for the labels, and then 1 for the test labels, and then it would be another 3 for the actual test image. That's just due to the pixels and how they're shaped compared to the labels, which would be their ID and then the article of clothing. So like 6 sweater, for example. Second, we're going to get the lengths of our training and our test labels. So as you can see, we have 60,000 images that we can learn from for our training data, and then we have 10,000 images of clothing that we're going to make our predictions on, and those are just the labels. The same goes with the images for each. And number 3, we're just going to show you some of the labels. As you can see, for our training labels, we're going to show the first 3 of our training and our test labels. We got a 9, 0, and a 0, which responds to the categories for the articles of clothing. 9 being an ankle boot, 0 being a t-shirt / top. And for the test labels, for the test data, we have 9, 2, and 1, which is an ankle boot, a pullover, and a trouser. And now, question 4 is going to show you the digital context of image 5 in our training data set, which is our train images. And as you can see, it is a crazy kind of matrix here that we cannot read at all, with the values 0 to 255 or 256. But it is very confusing for us, but that is how the computer reads one image inside of its array of pixels. All these data, specifically the zeros, represent a white pixel, and all the other ones are their color value and what shade they are. So on to question 5, just to give you a better visual example of what I was trying to say. You can see we have our training image right here that we have our digital content to. We're loading it inside of our fashion variable, and then we're going to plot that for you using our matplotlib library. So we're going to import that in as PLT, and we're going to want to show our digital content of our image that we stored in our fashion variable. And this right here, the cmap equals plot.cm.binary, just sets it so it's a nice black and white image. Otherwise, it's kind of like an infrared, it kind of looks like a weather storm to me. And this is just a little visually appealing and just easier on the eyes. So, and then we use the plt.show to actually plot our image and showcase it on the graph right here. We get this cool little pullover. And so on to question 6, we have the label for our image above. And what does it mean? As you can see, it is label 2. And if you remember, label 2 actually stands for a pullover. And you can see that would be a pullover sweater. At least that's what I would consider it. So that would be correct. And then number 7, we're going to see one of the testing images now. Once again, 0 being a white pixel, and so on and so forth, the numbers being a color shade to represent the shading of that. And we're going to plot this one just like we did our training image, just to give you a better understanding. We're going to store that into our fashion variable again. We're just going to reuse it. And we're taking our test image with the content above, and we're importing our matplot library. Once again, you don't have to because we did it above, but just doing it as a nice little visual reminder. And hey, if you want to plot something, you need this library imported. And then we plot it. Once again, the binary for the black and white. And this one is a little harder to understand. As you can see, it's a lot more blurry. It's not as clear as the first one. However, the label for it still thinks it is a pullover. And it is correct. It is a pullover. As hard as it is to see, you can kind of make it out. And that would be correct for the test and for the machine learning prediction. And so on to question 10. We're going to import some of our Keras library models. So we're going to import the models from it, and we're going to import the layers. So what we're going to do is we're going to define a sequential model, and we're going to store it inside of our network variable. And then we're going to reshape our array of the pixels into a one-dimensional kind of array. So we actually just want to have just the 2 columns. One would be, say, the labels, and then the other would be the actual amount of pixels in it. So we got the number of clothing and the pixels that make up the clothing. That 28 times 28 stands for the 784 neurons that we have that make up the pixel image. So we have that. We're just doing that for our training images and our test images. We are doing it to the shape of 10,000 because that's all that's in our testing, and we have 60,000 in our training. And as in the 20-minute video, we learned about the flatten method, in which it would do the exact same thing here for you as you have the images.shape we have down below, just so that you can have a better understanding. I like to have that little visual aid with me. It helps me understand it, helps me explain it, and I'm sure it helps you do the same. So what the flatten would do is it would take that data set and it would figure out the dimensions to have it to, one being the length of the data set and how many articles are in it, articles of clothing in this example, and how many neurons and pixels make up the image. And then we're going to normalize the image. As you remember, when we had the digital content, I can actually just scroll up for you, make it a little easier. We had the values from 0 to 255, and once again, it's very hard to read. So what we're going to do is we're going to have 2 methods. One from the video, which was we would import another library from Keras called utils, and we would say, hey, we want to normalize our images, and we want to put it in one axis. So what it does is it takes all the values, it turns it into a float value, and it divides them by 255, giving you anywhere from 0 to a maximum of 1 it would add up to in all the little values down below. And this is just another way that we did it from the textbook. You can see we changed the type to float, and then we divide by 255, and the digital content actually becomes what we see in here rather than the 0 to 255 scale. And continuing on, now we're going to actually teach our machine, and we're going to put it through our sequential method that we that we defined earlier. And what we're going to do is we're going to add this dense layer. We're going to have 512 neurons, and the activation is just going to be ReLU. And we run that, and then we're going to have it, and those actually do the weights, and they kind of just do the, I would say, hidden magic behind the scenes, where it does the calculations, and it transfers the weights, and tries to make an accurate prediction. And then we have it going through another layer, this time with 128 neurons, with more weights, just to better accurately predict what our image is going to be. And then lastly, we have our last layer, which only contains 10 neurons because we only have the 10 classification labels. And then our activation is going to be softmax. And I have a little mental note right here. It's used as the last layer because softmax returns a probability distribution, and it helps the program confidently make predictions. So under the hood, it converts all the values from the neural networks and the neuron into probabilities, and it sums them to 1, and it takes the highest numbers out of those, and that's how it confidently predicts. It says, hey, this one has 95%. I'm going to predict it is an ankle boot, for example. And continuing on, so now we have 2 actual ways to compile and run our optimizer. And our optimizer is really what we do when we cycle around inside of our neural network, just to readjust the weights and try and better adjust them to achieve a lower loss score and thus gaining better accuracy. So what we do is we take our model and want to compile. For the first one, we're going to use optimizer Atom, which we actually found out about in the video. Our loss is going to be a sparse categorical cross-entropy, and our metrics will be accuracy. And I actually split up, so if you forgive me, I'm going to just go a little out of order, but it'll make sense, I promise. So what we do is we compile that, and then we actually want to run and try and test our neural network. So what we do is we run the fit command, and we take all of our training images and the labels for what they are, and we're saying we want 10 epochs, which is cycles through our network. As you can see, the more it cycles through, the better the loss score becomes, aka the lower it becomes, kind of like golf, and the higher accuracy becomes. And now, I have, for the last one, I promise I will go back and it'll make sense. We evaluate the accuracy and the overall loss from this. So, if we use this method, we have a pretty decently large loss score, and the accuracy is about 88%, which isn't that great, but it is also a very difficult image set to kind of learn from. But what you see right here is overfitting. Because we run 10 epochs, it can confidently correctly guess what is in the testing, or the training data, rather, sorry. But when it comes to the testing data, it becomes less confident because it says, hey, I haven't seen this before. All I think the world is these 10 cycles through this training data. And it becomes less sure of the testing data. So now I will cycle back. If you remember, we have our second method for our optimizer, this time using RMS prop with a categorical cross-entropy, said it better that time, loss method. And once again, accuracy being our metric. So we would run this one instead of the Atom optimizer. And we're going to skip that. And what I have is I condensedly put it all into one little batch of code here, just for simplicity's sake. So it does all the steps that we've done up to this point. And what we need to do before we run our network fit is we actually have to change our labels to categorical so that our network can accurately predict them and kind of pair them with the label. And then we would do our network, we would run it again, epochs 10, we would just do 10 cycles, and we're splitting the batch sizes up into 128 so that the program can get through it faster. And as you see, the loss score starts very bad, very large, and it works its way down to a respectable amount, and it gets about 91%, which still isn't amazing. You could do much better for machine learning, but it is good because, once again, it is a test data set. It is very kind of difficult. We saw the one pullover. It was blurry, so imagine how computer feels. And then, so what we do, and this is kind of what we learned from this data set, or at least what I learned from this data set, rather, is kind of how machine learning works and starts making predictions. So the MNIST dataset in class was a lot more accurate because it's a lot easier to define a handwritten number. I know there were some confusing ones, But generally, the program can say, hey, I'm going to take this line, for example, and match it up with this, and thus it creates this number, that being a 0, that being a 9, that being a 6, yada yada. So in that, it more accurately guesses it towards a 99 percentile, which is really good. However, with the fashion one, a lot of the pixels around the outside, especially on the tougher ones, get blurry, and it can't really distinguish kind of the break in between those lines, I will say, of pixels. And it kind of groups them together instead of rather securing it separately, and it just makes it a lot harder for it to actually guess what it is and identify what it is in comparison to the numbers. And once again, we're going to just show you the loss score for this final RMS prop optimizer, and it's not great. 87%. The loss score is very high. Once again, I just talked about it. It's hard for the computer to distinguish. And once again, it is overfitting. Because we use the 10 epochs, it gets better and better at confidently guessing what's in the training data, but outside of the training data, it gets less and less confident the more epochs you go. Thank you for watching, and that concludes my assignment video.